Okay, this is Physics 7, April 14th, 2025, and we are starting chapter 21 right now. And just for the record, right, we finished chapter 21, and what you have to know, three very important things that you have to know. The B field is always proportional to the current in a wire, and something like that can be determined from Ampere's law. The magnetic field of infinitely long current carrying wire, is mu naught I over R. The magnetic field of the solenoid is mu naught I N over L, where N is the number of turns of the solenoid and L is the length of the solenoid. Okay, what else I'm going to put that here? The field is always proportional to the current in the wire, right? In the wire. The magnetic field, the equation of the magnetic field of a given configuration can be obtained from Ampere's law. Ampere's law. And those are three very important results. Okay, that's if you have to memorize anything, memorize this one right here. Always proportional to the current. The larger the current, the more intense the magnetic field is. Okay? And now, what we're going to do, we're going to start chapter 22. Start chapter 22. And let's not forget. Okay, I'm gonna be more specific here. In this case, is the field only inside the solenoid? Okay. You go. Magnetic field of solenoid of radius r. Okay, of radius r is, I don't like that. I'm gonna put like that. Yeah, okay, there's nothing I can do. For R less or equal than big R, okay? And then we have 0 for R greater than R. Like that. So there are two regions that you have to worry about that. Okay, and also the solenoid. The solenoid is the magnetic counterpart of the electric parallel plate capacitor, okay, which has a uniform electric field inside it. And now we can start talking about chapter 22. Keep that in mind. We're going to reuse it again. We're going to use all this information. And the law of electromagnetic induction. It's a very interesting result that we have out there. Let's review, right? Let's review the laws that we have seen so far. Magnetic force law or Lorentz force law. You got magnetic force law in a charge, in a moving charge. Gauss's law for electricity, which is just a more generic format of Coulomb's law. You go. Here's the electric field parallel to the area vector of your imaginary abstract surface that is enclosed an electric charge. Gauss's law of magnetism. Okay. Which is the magnetic counterpart of this law here. The difference being here that we have zero because there is no magnetic charge, magnetic monopoles. And we have Ampere's law, that the last one we saw. It's something like that. And we have one more law that that I'm going to formulate here for you. But first, let's see what is electromagnetic induction, right? What does it mean about electromagnetic induction? There is what does it mean, electromagnetic induction? What is electromagnetic induction, right? That's the question that you have to ask to you. Okay. Okay, the very basic, the easiest way to visualize this concept, okay, is by stating that electromagnetic induction is a way of inducing a current in a circuit without a battery. Inducing, let's say, a way of creating, right, a current in a circuit without a battery. That's the best way, the simplest way of understanding what the electromagnetic induction is. Not it's not the most generic concept, but we started there. You start to understand the electromagnetic induction by thinking in this way. Okay, so somehow we can induce a current in a circuit without a battery, without a power source. Let's put a battery. Okay. And there's more than one way of inducing a current in another circuit. So let me illustrate that for you. So here you go. We have a current loop, no battery in the circuit, okay? And somehow I make a current flowing through the circuit. That's what would be, electromagnetic induction. And let's see here if I can illustrate. Yeah, right in here. I'll get this one. Okay. Electromagnetic induction is when, electromagnetic induction is when you generate a current in a circuit without a battery. Okay, without, and I'm going to emphasize the without here. Oh, I did something wrong. Right here, without the battery. And let's see how we can do that. Notice that I didn't put the battery, right, in the circuit. A wire, yeah, let me show you what I mean by a wire. You go here, I have a wire. Okay. Here you go. I have a wire right in here. Right? I'm gonna close this circuit and let me okay. Let's see. Yeah, here you go. I got it. Here you go. I have a wire here. Right now, this wire, this circuit is open. It's not closed. So if I connect the tip of this probe to the inside of this connector, I have a closed circuit. Okay? There is a way. So what I'm saying about electromagnetic induction, I'm telling you that there is a way to make current flow in this along the circuit, within the circuit, without using a battery, without connecting it to a battery. That's what electromagnetic induction is all about. And how do we do that? Okay, how do we do that? It was discovered some time ago. Okay, that you can induce a current in a circuit. Okay, if you expose the circuit to a magnetic field. What I have right in here is the area vector of this field, of this circuit, okay? The circuit the plane of the circuit coincides with the plane of my screen. And I am arbitrarily stating that the area vector of this circuit is into the screen. So if I expose this circuit to a magnetic field, like this one, but it's not just a magnetic field, I may be able to induce a current in this circuit. And one possibility is by varying the magnetic field with time. That's one possibility. And let me tell you, this is real life, folks. Okay, what I'm talking about, this real life has practical applications. We use that all the time, and that's how we get our electricity at home with this type of effect, with this type of law. You change the magnetic field that a circuit is subjected to, and you end up, inducing an electric current. Okay, that's one way. That's one way of doing that. The story is a little bit more complicated, but but let's start this way for now. Okay, so let's write it down. One way without the battery. One way to do that is by subjecting a closed circuit, subjecting a closed circuit to a magnetic field, okay? The field that changes in time, okay? B as a function of t. That's one way. We're going to see other ways, and that's the easiest way. I can even show you some videos that illustrate this type of phenomenon. And let's see. Electromagnetic induction video, right? Videos. I want to see one. Okay, let's see here. That's the type of thing that we Okay, that's the type of, looks like this one here is a good one.
Fatura a partir de 80.000 e já cansou de taxas altas, enganosos e difíceis de entender, né?
That's the type of demonstration that I do in my classroom. Okay, here you go.
In 1831.
1831, right? Here what we have is a ammeter. Is that an ammeter? Okay.
Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction.
Okay, it was discovered in 1831. One guy in London, the other one in the States. Okay, and what did they discover at the time? We're talking about almost 200 years ago, right? Almost 200 years ago, 190 years ago.
I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops.
Okay, so do you see here what he has here? Coil with different loops, right? Or a different number of loops. One has 1 loop, another one has 10, the other one has 100.
I also have a bar magnet.
Here you go, a bar magnet. This bar magnet is going to be the source of magnetic field.
And I will start by connecting the single loop coil to the ammeter.
Okay, so here you go. So why do we need the ammeter? We need the ammeter to ensure to measure the current that's flowing through this loop. Okay, that's why we need this ammeter. Is not a source. This ammeter is just a measuring device to confirm that there is a current flowing through the loop, through the circuit.
The single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection.
Oh yeah.
Of the ammeter.
Watch it here. There's a very small. There's a very small deflection here in the needle. It's almost imperceptible. Okay. What is he doing? He's moving the bar magnet inside the loop. By moving the bar magnet inside the loop, he's increasing and decreasing the magnetic field that the loop sees, that the loop feels. Okay.
Of the ammeter needle.
Check it. Check the ammeter.
So now let me connect the 10 loop coil.
Now, what he's going to do? He's going to connect the same thing to the circuit to another loop, but now he has 10 loops. Because you have 10 loops, what you're going to see here, you're going to see the needle moving more than before. Okay. Connect one end.
To do the same thing. I'm going to move the bar magnet in and out of the coil.
Here you go.
Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic...
So that's how you change the magnitude of the magnetic field, by moving the magnet closer and further away from the circuit, okay?
Field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil.
Here you go. Now it's going to be 10 times more sensitive than the other one.
And I'll start by moving the magnet in very slowly.
See that?
Deflection to the right, pull it out to the left. If I move quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
It's possible. Let me put a link to this video here in the notes. It is possible to summarize this effect in a mathematical equation. Okay. See, for instance, the video. the following video. Wow, I cannot get a better link. All this junk here, right? Let's see if it works. Yeah, we get it. Okay, so we do get it. Okay, and it is possible, like I said, how can we induce a current in a circuit? Okay, that one way is by approaching or receding a magnetic bar to a closed loop. No need of a battery. But then there are other ways too. There are other ways. You can have a second circuit next to a first one, to the first one. Okay? When you switch the first, an electric, let's see, can have a circuit number one with a battery and a second circuit without a battery. Okay? When you turn on the circuit number one, the current is going to build up in the first circuit from 0 to a given value. This current is going to have a magnetic field that's also going to build up from 0 to a given value. And during this period in which the magnetic field is changing, it will induce a current in the first circuit. Okay? So just one different ways, right? With a magnet approaching and receding or changing the magnitude of the magnetic field, right? Here you go. That's exactly what this illustration here shows, exactly what that video showed us. We'll have here the loop, right? A closed circuit loop. I'm using here, in this case, I'm using a solenoid. We connect this solenoid to an ammeter, and then we get a magnet bar, okay? Closer and further away from the circuit. While the magnetic bar is at rest, no current flows through the circuit. But if I move it back and forth, the current is going to move back and forth as well. Here you go, induced current. The other way, that's the first way, right? By moving a magnetic bar. The second way that I stated in there is by having a circuit with a battery. Right now, the switch in the circuit is open. No current is flowing through the circuit. But the moment I close the circuit, there will be a very small amount of time in which the current is going to build up in the circuit. The current that's in this circuit has a magnetic field that's going to build up from 0 to a given value. And during this very small amount of time, there will be a current flowing in this circuit here. That's a second way of doing it, of inducing a current in another circuit. Okay. A third way. Okay, there's a third way too. It always involves a magnetic field, right? It always involves a magnetic field. You have to have a magnetic field in there. Another way of inducing a current in a circuit would be, here you go back to a circuit in a magnetic field. But in this case, you can have a constant magnetic field. You can have a constant magnetic field, right? The induced current is going to be 0. And then what you're going to do? You're going to change the area of the circuit. You're going to contract and expand the area of the circuit. Okay, it's possible to do that in real life. It's possible to do that in real life. The magnetic field doesn't have to change. The magnetic field doesn't have to change. But if you change the area, you are going to induce a current. Depending if the area is increasing or decreasing, the current is going to flow in one direction, and then the current is going to flow in the other direction. Okay? If the magnetic field is increasing, if the area in this case is increasing, the electric current is going to flow in one direction. If the area is decreasing, the electric current is going to flow in the other direction. Okay? And there is another way, which is the most practical way that we find out there. Devices are built in this exact way. Okay? Here you go. You rotate the circuit in a magnetic field. Rotating a circuit submerged in a magnetic field. Rotating a circuit with respect to a magnetic field. Okay? Let me illustrate that. Let's see if I have it. Okay, here you go. Do you see here the circuit? We have an axis of the circuit. The axis of the circuit, the B field is constant. And then we rotate the circuit in this field. Here you go. As we rotate the circuit in this field, the area vector of this circuit is going to change. And we are going to have an induced current in the circuit. Okay? Here you go. That's the very principle of the generator. The generator works in this way. Okay? We're rotating. One, two, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And again, a generator works exactly in this way. And we have that link that I showed to you. Let's see. Generator. Simulation. Let's see. Fat. This guy here. I like this guy. Okay, right in here. You know, you have seen something quite similar to that. You have seen an electric motor. An electric motor is, uses almost the same thing, but an electric motor uses a magnet bar, like this one that you see here, use a closed circuit, and get the circuit to rotate. The difference is that in the electric motor, we use a battery to generate motion. In this case here, is all the way around. A generator is something that transforms mechanical motion into electricity. Do you see here what's happening? Just by rotating this closed circuit, and in this magnet, we induce a current. Okay, look at the direction of the current here, right? And it is also inverting the direction depending on the point along the rotation. Okay, every half turn it inverts the direction. Okay, watch it. 4 different ways of generating a current, of inducing a current. That was the important discovery that Faraday and the other guy, Henry, managed to discover. Okay? This is the principle of the generator. Remember that. All these three different situations have one thing in common, okay? Have one thing in common. The current is the current is induced. That's one of the things that's common. But there is something else too. There is something else too, okay? And I want you to start thinking, okay? The one thing in common, the current is induced. But what is exactly happening there in the circuit, right? What is something else that is in common among those four situations, right? I'm gonna ask you, we're gonna play a little bit of a guessing game here, okay? And then another thing that they have in common is that a changing magnetic field, right? We're just playing here, exploring how we can find out what is common to all those four different, apparently different situations, okay? Do we have a changing magnetic field in all those situations here, in all those four situations? Let's see. By approaching and receding a magnetic bar here, the magnetic field is changing, right? I'm going to put it between parentheses. Changing a B field. Okay, here too, in the second situation that you turn on the circuit and there is a very fast buildup of a current and a very fast buildup on the magnetic field strengths, okay? Here also we have a changing B field, okay? It has a changing magnetic field. For items 1 and 2, right? Yes, right? What about the third one? By changing the area of a closed circuit, do we have a changing magnetic field here? In this case, no, right? B is constant. Okay. I'm gonna put that at the end. Changing B field. And this one too, changing B field. I don't need that here. And I'm going to emphasize by both facing it, changing B fields. In this case, B is constant. And here in this other case, B is also constant. Okay? B is also constant. So B field being a change of B field is not something that's common to all those four circuits, right? But not, okay? Yes, but not for 3 and 4. For 3 and 4 it is the area that changes, right? It's the area that changes. So now we have to start thinking what's common to all those four circuits? Okay, it looks like it is a combination of changing area with a B field. Did you notice that? It looks like it is this sort of combination. Notice that for the cases 3 and 4, there is a change in the area, which is resulting in the induced current. So that was the thought process that all those scientists start to go through to try to come up with an equation that would describe all those four situations. Okay? So it seems that the actual quantity that is inducing a current is a combination of a magnetic field with a changing, is a combination of a changing magnetic field, and or a changing area of the circuit. Okay? Did you notice that? B is constant, but area is changing, right? B is constant, but area is changing. B field changes, right? But area is constant. See that? And here you go. Here in the other one is the same thing for the first and second situation. Okay? B field changes, but area is constant. B is constant, but area is changing. It's a combination, not let's say, of the magnetic field. Let's put this way, with the area of the circuit, Okay, so after thinking very closely, very hard, right? Scientists came up with the conclusion after analyzing all these experimental results. Scientists have concluded that it is not the magnetic field or the area of the circuit that is the main culprit, right? That's the main quantity that is inducing the electric current. But something else that involves both the B field and the area of the circuit. At this point in time, you should already know which quantity involves a magnetic field and the area of the circuit. Do you remember? We saw that in electricity. Here you go. I'm going to give you some thought here, some time to think about that. Do you remember what B times A is all about? B times A, okay? If we create a new quantity called B times A, we can come up with an equation that will describe all those 4 instances in which the current is induced. And this quantity B times A has a name. It's called what? The magnetic flux. Okay? Symbol. We talked about flux before, right? But we talked about the electric flux. The magnetic flux is also important. Okay, and let me just put it here. There's something else here. Cosine of the angle between the magnetic field and the area vector. Okay. And here I'm going to put a theta. Did you get the idea? So what is important here is not the magnetic field alone, it's not the area vector alone, it's not the angle that the plane of the circuit makes with the magnetic field, but something else that we call the magnetic flux. Okay, so now we conclude. Conclusion. We conclude that the quantity in common for all these four situations, right, is the changing magnetic flux. Okay? If you have a changing magnetic flux through a circuit, you will be able to induce an electric current in this circuit, either by changing the magnetic field in time, by changing the area of the electric circuit, or by changing the orientation of the plane of the circuit with respect to the magnetic field. Okay? Theta here is the angle between the B field and the area vectors. That's the conclusion. And now we can resume everything in terms of a single equation. Right? Here you go. Recall. I'm going to here write the equation for the magnetic flux. Is the magnetic field, is the component of the magnetic field that's parallel to the area vector. Okay, and I'm going to put this cosine of theta on the other side. So if the change in magnetic flux this time is different of 0, we do have a current induced in our circuit. Okay? If different of 0, then you induce a current in a circuit. You will induce a current in a circuit. That's the whole secret of the creation of current without the battery. Okay, generators again uses this principle in physics. And I can go another step, okay? I'm going to write it in a different way. Here you go. We can start thinking in terms, not just in terms of current, but in terms of the voltage, induced voltage, an induced voltage that's going to generate an electric current in the circuit. And there is this negative sign here. This negative sign has a very important interpretation, okay? And we are going to discuss that. That's the actual law that we right? If we use Ohm's law, we can rewrite this equation in terms of the induced current. So now I'm going to write it down in this way. Here you go. Can you remember that? Okay. So in summary, the changing. So in summary, a changing magnetic flux through a circuit induces a current. This changing magnetic flux, B flux, okay, can be achieved in 4 different ways. We described above. by changing the B field, by changing the area of the circuit. This change in B flux can be achieved in 3 different ways, right? 3, not 4, 3 different ways. By changing the magnetic field, by changing the area of the circuit, and by changing the orientation of the area of the circuit with respect the direction of the B field. Okay? And we do that by rotating. We do that by rotation. And it's at this point that I want you to recall the principle of the electric motor, right? I want you to recall the principle of the electric motor. In this case, we input an electric current, and the output, we input an electric current that changes in time. An electric current that changes in time. And the output is a motion, a rotation or oscillation, okay? In the case, here we go. In the case of a generator, in the case of the generator, in the case of a generator, we have very opposite principle. Okay. We input motion to a circuit, right? And this circuit output an oscillate, a variable current. So if you understood how the electric motor works, so if you understood, right, how the electric motor works, you will be able to understand the principle of the generator, which is the exact opposite, using the same devices, right? And that is, that's the equation that you have to have in mind. Now, what time is that? 10:40? Let me take attendance now. Any questions about that? Again, that's very important. It's a very important principle. That's, wow. Okay, okay, so you just had a 6th earthquake in the air. Oh my goodness, I'm scared. Did you folks feel this earthquake there in Los Angeles? We had one just recently there nearby nearby San Francisco, right? I just saw your message here.
By San Diego, it was a 6.0, give or take.
Oh, it's very strong, right? Did you manage to feel that in Los Angeles? Because a 6.0 earthquake in San Diego, I believe you would be able to feel it there, right? In Los Angeles.
I did in Inglewood.
What did you say?
I felt it in Inglewood.
Oh, you did feel it. Oh my goodness. 6.6 or 6.0 is a very strong one. Apparently it was 2.8 in Los Angeles. Okay. I only saw your message now, Ramon. I only saw your message now. Got like 3 alerts, so you must be very, very scared there.
The one weekend that I'm out here, this happens.
What did you say?
The one weekend that I'm out here, this happens.
3 alerts. We don't have earthquakes in Brazil, We don't have earthquakes in Brazil. We don't have hurricanes. We don't have any of that in Brazil. Oh, well, I hope everybody is no longer freaking out, right? Everybody is now Keep me updated. Let me know if you feel anything else there. Okay. My first earthquake was back in 1998, 1999. Okay. I was living in Torrance. The first earthquake I felt in my life, 1998. Like I said, in Brazil, we do not have earthquakes, so I had never felt an earthquake until I moved to Los Angeles. And it was 2 o'clock in the morning. I was sleeping. I used to live in Torrance. I was living in a building that was made of wood, right? And 2 o'clock in the morning, I felt the building oscillating back and forth. You know, it's just making the woods were making that noise, nyek, nyek, 2 o'clock. I woke up, went outside, and waited until everything calmed down. It was kind of scary. And then another one I saw, it was like 5.0 in Santa Monica, but never a 6.0. Wow. Okay. So let's go for the attendance, right? Let's take attendance here. Today is the 31st. Let me see here. Okay, 31st was Cesar Chavez Day, right? Okay, that's a holiday. 7th of April was a spring break. Okay, holiday and holiday. So Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Next is Nestor Alvarado. Are you there, Nestor?
Yeah, I'm here.
Okay. Monte Ambarshan.
I'm here, Professor.
Okay, thank you, Monte. Isabella Ballesteros.
Here.
Thank you, Isabella. Justus Bolden. Thank you, Justus. Next, Alexandra Burmistrova.
I'm here.
Thank you, Alexandra. Next is Benjamin Carvajal. Thank you, Benjamin. Brianna Carrillo. I don't see Brianna. I suspect, let's see, I suspect that she dropped, right? Brianna. Yeah, Brianna dropped. Oh, yeah, that's right. I was forgetting. Yeah, thank you for reminding me. Let me take out here. And okay, yeah, so let's go here. Exam. Exam 2, right? Abir, what do you prefer? Do you prefer this week, the day after tomorrow, or you prefer the exam next week?
I'd say next week.
Next week? Okay. So, Nestor, what do you prefer?
I'll say next week.
Next week? Next week, right? Let's put here next week. Next week. Monte, what do you prefer? The day
Next
after
week,
tomorrow?
please.
Next week, okay. Isabella? Isabella there? Okay, I'm not hearing from Isabella. Let's go next one. Justus, what do you prefer? The day after tomorrow or next week? Justus. Hello, Justus. Sorry, I just went. Okay, next week. Okay. Alexandra, next week or the day after tomorrow?
Next week, please.
Next week. Okay. Benjamin, next week. Okay. Next is Elizabeth Castellano.
Here.
What do you prefer? Next week or
Next week.
next week? Okay. Next one is Natalia Cordoba. What do you prefer? Let's see if Natalia is here. Yeah, Natalia is here. Can you hear me, Natalia? Okay, I'm gonna put a star here in Natalia's name. Jacqueline Delgadillo. Next week or the day after tomorrow?
Next week would be fine.
Okay, so we go. And next, Jenny Diaz.
Here.
Yeah, next week or the day
Next
after?
week?
Yeah, okay,
Yeah.
good. Valerie, thank you. Valerie, thank you, Jenny. Valerie Diaz.
Here.
Yeah, next week or the day after tomorrow?
Next week, please.
Okay. Juan Escalera. Let's see. It doesn't look like Juan is here today, right? Juan Escalera. It looks like he dropped. I don't see it here. No. I'll keep it. Bianca Eloki.
I'm here.
Okay, next week or the day after
Next
tomorrow?
week, please.
Okay, next week. Edwin Gonzalez. Edwin is not here. Yeah, doesn't look like. Eli Gonzalez.
Here and next week would be amazing.
Okay, thank you. Next one, Manuel Hernandez. I'm here and I would prefer this to be next week. Okay, okay, we can do that. Let's see, someone's trying to get in. Samantha. I don't think Samantha is here. Next is CJ. I don't see CJ here. Luis Leal. Yeah, Luis Leal is not here. Amber Lopez. Next week, okay. And Adeli Lopez.
I would say this Wednesday.
The day after tomorrow.
Yes.
Okay, prefer the day after tomorrow. Day after tomorrow. But can you take it next week, Adeli?
Yes. I would just have to enter a little bit later because I have another exam scheduled that same day.
Okay. Okay, let me. Okay, Genesis Lopez. Okay, so good to know. That's good to know. Genesis Lopez.
I'm here. I would like to take it next week.
Next week, okay. Mary Michaelian. Okay, do you prefer next week or okay? Galia. Okay, right. I don't see Sebastian. I don't see her here. Ramon Olivares.
Here. Next week, please.
Next week, okay. Next is going to be Taylor Forn. I don't see Taylor. Next is Jeremy Pittman. Okay, okay, good. Juan Escalera next week. Okay, Juan Escalera. Why? What's going on here? Yeah, for some reason, your name is not listed here. Huh, strange. So let me put it here. Insert escalera. Escalera with E. Oh, yeah, here. Okay. Next week. Good. So, Natalia Cordoba, right? Let me go back here to Natalia. You prefer, let's see, Natalia next week too. Let's finish. See here, Jeremy Pittman. I don't see Jeremy here. Edwin, right? Edwin, what's your last name, Edwin? Edwin Gonzalez, right? Yeah, Edwin Gonzalez. Yeah, okay. Do you prefer the exam next week or the day after tomorrow? Next week, okay. Stephanie Ramos.
I'm here. And if we could do it next week.
Next week, okay. Leslie Rios.
I'm here, and we can do it next week.
Next week, okay. Jason Strait.
I'm here, and we can do it next week.
Next week, okay. And Hema Torres Navarro.
I'm here. We can do it next week.
Next week, okay. Okay, so let's do next week, and that student stay after office hours, okay? That student that Arely, right? You said you have to arrive a little bit later if it's gonna be next week, is that right? Yeah, I don't hear from Arely. Okay, so okay, stay if you're hearing me, Arely, stay around for the office hours, okay? So we can talk quickly about that. And okay, let's postpone it to next week. I'm gonna do that in the syllabus. Exam 2. Right in here. This one. And then we will have lab 4. Lab 4, this one is going to be the topic. AC circuits 2, I think it's okay like that. And I'm gonna save it for version 11. Don't forget the material is going to be the same, chapters 2021, labs 1 and 2, okay? You can have access lab 3. Okay. Okay, we'll talk about that, Ramon. Okay, we'll talk about that later on. So break, we're gonna have our break right now. Break from 10:55 a.m. to 11:10 a.m. Okay, so I see you in 15 minutes. I'm back here. And what was missing there? There's one minor thing missing in my notes here, in this equation that you see right here, okay? So what's missing is n, the number of loops, okay, in the circuit. The more loops you put in the circuit, the more sensitive it will become to the induced current, okay? And you saw that in the video that I showed to you. Here is the link for the simulation of the generator. It's, I want you to review that. It's a very good simulation. I like it. I like the way they do it. And what I want to do, let's do some examples in the book, right? There is that situation which we have emotional EMF. EMF stands for electromotive force. Electromotive force is just a different name for the current generated by the induced magnetic field, by the induced electromagnetic induction. By the electromagnetic induction. Okay, so here you go. Let's do. We have this example here. Let's see. Yeah, that's it. Let's do example 1 here, right? So here you go. We have you can picture this situation like a railroad, right? 2 conductive plates, and then you have a train that moves along this rail. Okay, and let's say we connect a light bulb to the ends of those 2 rails. Since the Earth has a magnetic field, you could, in theory, you could induce an electric current in the tracks, in the tracks of the railroad. Okay, just by moving your train along this rail. Can you picture that? So let's solve a problem like that. So consider a closed circuit whose area with a changing area, right? Whose area changed. Let's see. It's better if we can make a drawing here. I'm gonna copy that.
Well, I know for a fact it wasn't me. Who signed it? Can you read the signature? It's kind of hard to read, but I can definitely see an L, an A, and an N in the signature. Is there any way Adam would have signed this? I can't speak for him, but I'll definitely check. Okay, and I'm gonna go pull footage. I'm gonna interview every single staff member that worked last night, including my assistant and the bar manager. I'll call you with anything I find out. Okay.
Here you go. Consider the circuit below. Here you go. The circuit below.
I didn't sign anything. Me neither. But somebody who wasn't us signed for the approval for all the.
We have 2 conducting wires parallel to each other and separated by a distance L. Okay. There is a B field of non-intensity B pointing into the board, right? Into the board. The bar on the right is moving with a velocity v. Find the induced current in terms of the other parameters. Okay, example. Treat that as though as an example. I will solution. Okay, so here you go. We gotta use we need something else to consider the circuit below. We have two conducting wires parallel to each other, separated by distance L. Distance L. There is a B field of non-intensity B pointing to the board, and a light bulb of resistance R, right? Connected to this circuit. The bar on the right is moving with velocity, is moving with velocity v. Find the induced current in terms of the other parameters. Okay, so the equation that we have to use is, oh, not this one here, is the one that is the law of induced current. Okay, and in this case, it's just one loop, because here you go, the loop is this one that you see right in here. Okay, that's the loop. You have just one loop, so we can move this thing out. By the way, I have to say that there is a uniform, okay, I gotta put it here. There is a uniform B field of no intensity B. So my magnetic flux is going to be given by BA. This magnetic field makes a 90-degree angle, is the plane of the circuit. So there is no angle there to worry about. And on the top of that, what else? You know, on the top of that, we have like an initial area A naught plus VT, right? Okay. That's what we have here. See this guy here. Like that. And now we have to replace here we go. We have to get this thing inside of this place here. You go. Like that. That's the magnetic flux, right? Magnetic flux, you go. The B is a constant. Consequently, this B factor here can be taken out of this delta T, delta T. And now I'm going to need only one parenthesis. Okay. We apply this operator here. We got to break it down. Delta A naught, delta VT. Like that. I don't need this second parenthesis anymore. I'm going to write that down in terms of two terms, delta A naught over delta T. Oh, not like that. And here we are going to write this one as well in terms of delta T. And I put a parenthesis here now. Okay. Don't forget the left side of my equation. I'm trying to find this guy right here. Okay. Okay, delta A naught is going to be 0 because A naught is a constant, okay? So delta A naught is going to be A naught minus A naught. That's what it is. Initial A naught, final A naught over initial A naught, which is the same. It doesn't vary. Okay, so this delta A naught should be like, final A naught minus initial A naught. But the initial area was at that instant of time equal to 0. And it doesn't change as time goes by. So this A naught here must be equal to this other A naught. In this case here you go, V can be taken out of the delta symbol. And now we have delta T over delta T. So what we end up having? We end up having here a term that's equal to 0. And another term that is equal to 1. Okay? And we finally get something like that. BV. Am I forget? Oh yeah, I'm forgetting something here. Let's see if yeah, I'm forgetting something here. I've just got okay. So what am I forgetting here? Initial area minus. Okay, there's something. Let's see if I can get the illustration here for you so you can see it better. Okay, right in here. This one. Okay, that's the type of problem that we're doing right now. That's the type of problem that we're doing right now. Here you go. Moving with velocity v. The resistor is the light bulb. The magnetic field is into the board. Okay, the distance here is L. So what is happening here? Let's see if I have a. Yeah, okay, I want this one right in here. Okay, so that's the small distance that it travels. Okay, so the additional area is going to be VT times L. That's what's missing there. That's what's missing there in my equation. Okay, VT times L. I can even write down a different way. Let's see, initial area. I can put like that, initial area. Another way of writing the same equation. Initial area plus delta area, like that. Okay? And the delta area is going to be equal to the distance traveled by the bar times the width of the track, which is the distance L. Okay? So here you go. I gotta put L here. I gotta put L here. I gotta put L here. When I take out VTL, right? And here we put VL as well. Here is VL, and here is VL. That what you see right in here, don't forget, what you see right in here is the induced electromotive force, induced voltage. Okay? Just by having a contraction like that, you can produce electricity. Okay? that's going to be given by the magnitude of the magnetic field, the velocity times the distance between the tracks. Now, if you want to know the current, you have to replace the induced electromotive force by the resistance times the induced current. And then finally, we have this result here. BVL over R. This negative sign has an important interpretation, okay? The negative sign has an important interpretation. And what's that? That's where the Lenz's law comes about. It's not difficult. It's not difficult to come up with an interpretation. The negative sign tells you, the negative sign has an important interpretation and tells you the direction of the current. Okay? Tells you the direction of the current. Given by Lenz's law. And I'm going to put it law between quotes because it's not exactly a law. Okay. Lenz's law. And let's see how it goes, right? So now here you go. We can do the consider circle below. We have two conducting wires parallel to each other. There's a uniform B field of non-intense B point up, the bar up. Find the magnitude. Let's put here the magnitude of the induced current in terms of the other parameters, right? So since you want the magnitude, we can drop this negative here. I'm gonna put it magnitude here. Yep. And that would be example, what's going to be the direction of the current, right? Example 2, find the direction of the current in the above example. And then I'm going to explain to you how we find that out. Okay, solution. The negative sign in Faraday's law Okay, don't forget this is called Faraday's law. Yeah, Faraday's law. Tells you the direction of the current. And how does it, how do we interpret that? And we interpret that in the following way. And we interpret it in the following way. Okay. The current will flow in the direction of, in a direction contrary, here you go. In a direction contrary to the change in magnetic flux. Okay. If magnetic flux increases, the current will flow in a direction contrary to the direction of the magnetic field, Okay, here you go. If the magnetic flux increases, the current will flow in a direction contrary to the direction of the magnetic field. Okay, now the other one is if the magnetic flux decreases, the current will flow in the same direction, of the magnetic field. And by the way, as given by the right hand rule. Okay? Gotta put that in both. Right hand rule. So let me show you how we do that. Here you go. In this case, the magnetic flux is increasing. Okay? In this case, the magnetic flux is increasing because the area is increasing. Okay, so here you go. Let's write that down. In this case, the flux is increasing because the area of the circuit is increasing as well. So we use the right hand rule, contrary, in a direction contrary to the B field. Okay, so how do we do that? We point, here you go. We do the following. One, point the right hand thumb opposite to the B field, and two, check the direction the palm of your hand moves. In this case, here you go. Magnetic field is into the board, consequently, right thumb must be out of the board. Now look at the direction of motion of your right hand, the palm of your right hand. It goes in the counterclockwise direction, okay? Okay. Counter, in this case is the counterclockwise direction. Okay. That's a very simple rule. Okay, and if the bar starts moving towards the lamp, it's going to decrease, right, the area. Consequently, the current must move in the clockwise direction to help the magnetic flux. As the magnetic flux decreases, the current should flow in a direction to help the magnetic flux. Okay? If the magnetic flux increases, then the current should flow in a direction to counter the direction of the magnetic field. That's how you find out the direction of the current. Okay, that's an example that's treated in the book. And BVL over R. Okay. And now we can do the same thing for the generator. Okay. We can do the same thing for the generator. In the case of the generator, okay, here you go. In the case of the generator, I'm gonna just treat it quickly. We're not going to do step by step here because we need calculus to do something like that. Okay, in the case of a generator, the situation is the following. One, the direction of the area vector changes with respect the direction of the B field, like that. Okay. And here you go. And B flux is given by, we did that before, right? Here you go. I'll write in here. That's the equation. Here you go. dA cosine of theta. But this theta angle is changing as time goes by. We, in practical circumstances, we use a uniform rotational motion. So this angle theta has a uniform angular velocity given by omega t. Okay? It's going to be like that. Flux through the area of the circuit. And then, here you go. I'm going to get this one right in here. Like that. It's just one loop. Okay. We're going to put that equation of the flux right in here. B doesn't change, A doesn't change. Consequently, we can take it out of this delta symbol. And we have this delta cosine omega t and delta t, okay? Okay, it happens that, this type of relation that you see right in here is, we can obtain only through calculus. And delta cosine of omega t over delta t is going to be given, I'm going to give you the result. It's going to be minus sine, and we're going to have also a omega term right in here. That's what delta cosine omega t, delta t is, okay? Like that. And now let's continue here with this equation. This negative sign cancel out with this negative sign. And the current now is going to depend on the frequency of motion, on the frequency of rotation of your circuit. Okay? So here you go. Divided, I'm going to put divided by omega here. I want to put the omega elsewhere. Okay. My omega was in the wrong place. Now I can put my resistance right here. And look what we get. We get from the above, note that we get a current that changes direction as time goes by. Okay? the current is gonna flow in one direction while the sine omega t is positive. The sine of omega t goes, the sine goes from 0 to 1, right? From 1 to 0. And from 0 to -1, -1 back to 0, right? That's what happens. And what does it mean? Negative values for the current means that the current is moving the opposite direction. I can plot this graph for you right here. You go. T. I'm gonna say, here goes sine. I want to put sine of t. I'm gonna make it very simple for now. 0. I'm gonna do like pi over 10. Even better. I'm gonna do like that. And 1, 2, 3, right? Go. I'm gonna plot for you a. Now I gotta do this. Ooh. Insert down. I'm gonna put a time t equal to 0. We're gonna have n equal to 0. Okay, so what am I doing here? Times. I'm kind of automating this process. Okay. Here you go. Here's the instance of time that we have, and I'm going to determine the sine. I'm going to do even better here. I'm going to put it omega t equal. That's going to be symbol. I'm going to plot in terms of omega t, okay? Not in terms of t, but in terms of omega t. And now instead of seconds, we have a unit of radians. Let me move. Yeah, here you go, better. And you go. There's no unit for sine of omega t. I'm going to copy and paste here to make my life easier. Now we can put 1, 2, 3. Oh, heck. Ay. Okay, I gotta do it the right way. Symbol. Okay, now we have it. And then omega t. Okay, so here we go. And now we are going to plot. That would be the model of my my mathematical model of the current. Okay, so here you go. It looks just like that. So initially at time t equal to 0, the current is equal to 0. Okay, and then as time goes by, the magnitude of the current, it keeps on increasing until it reaches its maximum value. That's how you should interpret that. And then, the current keeps increasing, right? In a sinusoidal way. And then after reaching the maximum value, the current is going to decrease in value until it goes back to 0. Soon after passing this instant of time, the current is going to change direction. It's going to be something like that. I'm going to do the movement of the current with my hand, okay? At a given instant of time between 0 and maximum, right? 1/4 of the way, the current is going to have maximum value. And then after reaching the maximum value, the current is going to slow down until it comes to 0. And then it's going to reverse direction. It's going to keep oscillating back and forth. Okay? Here is a full cycle of the current. Up to here, the full cycle of the current. So the current is moving back and forth in your circuit, back and forth in the circuit. Okay, between this instant of time and this instant of time, the current increases in one direction, then keep on moving in the same direction, but then the velocity starts to decrease, goes to zero. Once it goes to zero, it changes direction and the magnitude of the current increases. Okay, it could continue moving in the opposite direction until it gets to zero again, and everything is repeated. So that we can, we can visualize this current just by making your hand move back and forth, like in a circle. That's a very good way of visualizing how the current behaves in a circuit. In a circuit of a generator. Don't forget, this is the circuit of the generator. Okay, so in the case of the circuit of a generator, right? The current, the following happens to the current. One, at time at t equal to zero, the current is zero. Two, soon afterwards, the current is positive and it is increasing in magnitude, like that. Until it reaches a maximum value equal to BA omega divided by R. That's the maximum value of the current for this specific case. Don't forget the current depends on the frequency of rotation of your circuit. I'm going to put that in italics and italics. Okay. Yeah. Any questions? I heard someone saying something. Okay. So let's move on. Okay. Soon after the current is positive. And soon after the current becomes positive, right? Becomes positive, comma, it increases in magnitude until it reaches a maximum value equal to BA omega R. At this point, the current keeps on moving in the same direction, but with decreasing magnitude, like that, with decreasing magnitude. Increasing magnitude, decreasing magnitude. Okay. When the current reaches, when the current reaches zero, because of this term here of sine omega t, right? Comma, it reverses its direction and becomes negative. Okay. The magnitude, right, of the current increases, the magnitude, don't forget the magnitude of the negative current increases, right? Of the negative current increases until it reaches its maximum value, like before. Maximum value, comma, BA omega. At this point, At this point, we go, just like before, at this point, the magnitude of the negative current decreases until it reaches 0. And everything repeats. Everything repeats as before. Repeats as before. That's the picture you must have. Okay. The current is initially 0, and then and the motion of the current. So what's the motion of the current? Is the value of the current? What's that? Is the motion of the electric charges, right? So the tip of my finger can be the electric charge that's moving. So moving like that, move like that, move, right? You start at 0, increases its speed, reaches maximum speed, decreases its speed, but it's moving the same direction. When it comes to 0, then it reverses direction. That's what's happening to the tip of my finger. And that's a very good model of the motion of the electric charge in a generator. And by the way, the current because the current in the generator, because the current in the generator changes direction, okay? We call this type of circuit alternate current circuit. Alternate current circuit. And it is, we say that's AC. Okay? Alternate current circuit. Alternate because the current is changing direction. So we have two types of important circuits. One, direct current, we call it DC, current that moves in a single direction, like the circuit with a battery. And two, alternate current, AC, the current moves, the current alternates its direction of motion, like in the case of a generator. Okay. The electricity that we get from the wall, right? In our houses is AC. The current, right? Is AC current that changes direction. 1155. Now, do you understand why I skipped the alternate current in that chapter? Right? First, we have to talk about the generator. We have to talk about the generator. That's why I skipped the current before. And you needed to know about the law, the Faraday's law of electromagnetic induction. Okay. So here we go. Remember that. Okay. So in summary, in a DC circuit, the current is constant. Okay, I is, let's say, constant in a AC circuit. The current varies sinusoidally with time. Sinusoidally with time. With time, so it's gonna be I is proportional. Let's see here. I gotta get that. And for an AC current, we usually represent the current with a lowercase, okay, instead of uppercase. And I'm gonna put it here, proportional. Proportional to sine omega t. Okay. Capital I denotes DC current. Lower case I denotes AC current. That's how we usually do it. And 11:58 now. I think I'm gonna go. Any questions about that? Let's take a quick look here in the book. So now we are ready to talk about, let's see, not this one, right? This one here, alternating current. Now we are ready to talk about alternating current. But only after we go through chapter 21 and start chapter 22. Okay? This law, Lenz law. Electric generator. I already told you about the electric generator, right? And then I need to talk about mutual induction. That's how we're, okay, that's the situation is the following. I already covered 22.1. I covered 22.2. I told you about magnetic flux. I told you we covered 22.4. I told you 22.5. We're going to skip this one. I already covered 22.7, and now we have 2 more to go. Okay, so let me copy and paste. Okay, induced electromotive force, 22.6. Let's see, 22.6 is applications of electromagnetic induction. Okay, applications of electromagnetic induction. To sound, right? We're skipping that. So we cover all of that, and now we are left with those 2 sections. Let's have our break now. Break 12 noon to 12:15. Any questions before we go into the break? Okay, so I see you in 15 minutes. Okay, I'm back here. And so let's go back to our equation, to our law, our Faraday's law. This one right here. Now we're going to talk about mutual inductance and self-inductance. Okay. Okay, mutual, these two quantities, okay? These two quantities are intimately connected with the definition of capacitance, okay? Recall that the definition of capacitance is what? Capacitance is Q divided by delta V, right? And I mentioned the two are intimately connected with the definitions of capacitance and resistance. Okay, gotta put that resistance here. And resistance. Capacitance is something like that, right? And resistance. What is resistance? V over I. Like that. I mentioned before that both quantities, although written in terms of Q, V, and I, are related to their geometrical parameters. Okay? The same applies to mutual and self-inductance. Same applies to mutual and self-inductance. Okay, and but mutual and self-inductance are defined differently, okay? In a different way. Let's put Q over V instead of Q delta V, right? Let's put it like that. These two definitions are derived from Faraday's law. Faraday's law. Okay. And I'm going to so in order to understand those two concepts, you have to picture two solenoids in a circuit. Let's see. Let's see. We go. And do you see here the electromotive force? The electromotive force is exactly the same, right, as the voltage, right? Even though I put it in a different format. Okay? Even though I put it in a different format. But it's no, there's a very close parallel between those three quantities. And also remember what I mentioned before we go talk about the two solenoids, right? Also recall what I said at the beginning, what I said at the beginning of the course. what I said about the three basic devices in electricity and electronics, right? It's going to be the capacitor, the resistor, and the inductor. The other one is the transistor. Okay, not covered in this course, not covered in this course. So we are coming to a point where we are covering this third important device, the inductor. Okay, which is represented the capacitor, the symbol of the capacitor, symbol is the parallel plate, right? Capacitor. The resistor, you know, just that line, right? That zigzag symbol. Symbol is a zigzag line, And the inductor, what about the inductor? The symbol of the inductor symbol is the cylindrical. I mentioned that before, right? Let's take a look here. The one that has a constant magnetic field. What's the name? It's a solenoid. The symbol of the inductor is a solenoid because it's the simplest inductor that we are going to see out there. By the same token that the parallel plate capacitor is the simplest capacitor we are going to see out there. The symbol of the inductor is the cylindrical solenoid. Okay. And now let's take a look at the inductance, right? And see here, electromagnetic induction. Here you go. That's okay. So that's where we want to look at. Consider a solenoid of length L and in turns connected to a generator. Okay. And now consider a second solenoid which has no power source whatsoever. We call this one here the primary solenoid. Primary solenoid. Now consider a second one that's inserted inside the first one. And it has no power source whatsoever. We need this configuration to start talking about mutual inductance, okay? Mutual inductance and self-inductance. We need this type of configuration for you to. This one, the primary one is a length L. The secondary one has a length L prime. Okay. This one, remember, there is a current flowing back and forth here in the primary one. The current is changing in time. And because the second coil is inside the first one and it's feeling a changing magnetic field, there will be a current induced in the second one, right? Can you picture that? Okay, so I'm going to, let me copy that so we can follow the thought pattern in terms of these pictures. Ideally, we should be doing experiments with those things. Okay, that's the best way of understanding the theory that we are covering. And I cannot overemphasize. It's difficult to overemphasize how important something like that is. Okay. First one, and not connect to any power source. Okay, two solenoids, one that's connected to a generator, a second one, which is in a closed circuit with no power source whatsoever, the secondary coil. Now, I'm going to say that the primary coil, the primary solenoid slash coil slash solenoid has NP turns. NP turns for primary. NP, right? P subscript here is for primary. And the secondary coil has NS turns. The voltage across the first coil is going to be given by something like that. Here you go. By the same token that the current can be given by, IP, I naught sine or cosine, depends how you're taking the time. The voltage also is going to be given by that. Okay, and there must be, to be completely correct, I have to put a little phase here in this guy. Okay. Now we can. Okay, according here you go. According to Ohm's law, what do we have? We have that Vp is going to be equal to Ri. And I'm going to put it like that, sub P. And the resistance is going to be R. And I'm also stating that this solenoid, the reservoir resistance, the primary solenoid, here you go, the primary coil solenoid has NP turns and internal resistance R and an internal resistance R. Okay, and the secondary coil has NS turns. NS turns. Okay. Let's see, V equal to Ri. Oh, I gotta put this way. Don't forget that V is equal to Ri, according to Ohm's law. Consequently, my current in this circuit, it is going to be Vp of T Vp over T divided by R, like that. And, oops. Did I get it the right V? All right. That's what I want. I want like that. Here you go. That's how I want to write. And now, V naught. I have to do all of that to come up with the self-inductance and mutual inductance, okay? V naught is the maximum value of the voltage. And I also going to, let's see, I'm gonna put that subscript P here to remind you that this is the resistance of the primary primary coil. I'm gonna put it here, R sub P. Okay, and I'm gonna rewrite it in a simple way. Now I'll take out this sign, put it right in here. And now this term that you see right here, I'm gonna call it I naught. I naught of the primary. Like that. Okay. Remember, I mentioned to you before that the B field of a solenoid is uniform and given by something like that, right? Where this N here is just the number of turns per unit of lengths, mu naught I. Okay. Okay, remember also a current that changes in time also produces a magnetic field that changes in time, right? Can you picture that? So consequently, what we are going to have, instead of n prime, here's for a genetic, right? For a genetic device. Consequently, the magnetic field of this primary coil, and I'm going to put B sub P, is going to be given by N, so sub P, I sub P. Okay? I sub P. I'm going to simplify by notation. Instead of N sub P, I'm going to denote it for the lowercase n sub P. And let's not forget that this current of the primary coil is a function of time. Consequently, the magnetic field is also going to be a function of time. And we found that this current is going to be given by this thing here, where this guy here is a constant and the time dependence is this one that you see right in there, in the sign. So here you go. Let's write that apart. B of the primary coil inside the coil is going to be given by this term that you see right in here. I'm going to simplify my notation, okay? And I'm going to drop this P. Simplify my notation, I'll drop. We simplify the notation by dropping the P. Simplify the notation by dropping the P in the current. The current. What else? Okay. Now that we got the magnetic field of the first coil, we are going. Let us get the induced voltage of this primary solenoid or coil. Okay, the induced voltage, all you have to do is to apply right in here. Faraday's law. Faraday's law, right? This one right in here. And where this N is NP. And this B is this flux magnetic flux is the magnetic flux of the primary coil. That's the electromotive force induced in the primary coil. Okay? But because the secondary coil is inside the primary coil, we must have the same relation for the secondary one. Okay? The V induced is also going to be given by the same equation, but now with the subscript exchanged by the secondary coil. Okay? The electromotive force is going to be the same for the two coils. And now we have this relationship right in here that's important, just to get to that point of mutual inductance and self-inductance. Here you go. Right? In the next step, this negative signs cancel out. Okay. Let's not forget. Now I'm going to do something that I used to do on reverse. I'm going to put my number of coils here inside this operator, delta delta T operator. Let's put the parentheses here. And then I'm going to copy this one, put it right in here as well. But now I have to change the subscript, right? And here you go, secondary. And then we get a simpler, even simpler equation. Here you go, this term here must be equal to the other term. Okay. And now I have to rewrite my magnetic field. I have to rewrite my magnetic flux in terms of the magnetic field. Okay, and here you go. What we have right in here is going to be BA, B primary, as a function of time. And don't forget area. And I have to put the area of the primary. Okay, I'm going to go another step. I'm going to write down this term here in terms of the, don't forget that the magnetic field is always proportional to the current, right? So because of that, I'm going to write that down in a simpler way. I'm going to write that down in terms of a constant of the primary times the current of the primary coil. Like that. And then we can go another, let's see. And by the way, this constant, you already know is equal to what? We're talking about the solenoid. This constant is just like that mu naught n, right? I. And by the way, it should be the primary. Now I want you to pay attention to what we have here. We have parameters that are a function of the geometry of the solenoid, right? The area, the number of turns, and the number of turns per unit length, and the number of turns. Okay, I want you to pay attention to that. We are getting to the point where we are going to come up with what we call today, what we call this one. Let's see, this one here is supposed to be upstairs. Here you go, it's supposed to be upstairs. Okay. And I'm going to get this term that you see right in here on the other side. Flux. Let's see, we should have N over S as well. Let's see. I'm gonna put N over S here. Here you go. Yeah. N over S. And I'm going to rearrange. This term is gonna go right in here. This one should be here. Okay. And then what else? Everything that I have right here, all those constants that we have right in here, I'm going to call the constant big M for mutual inductance. Okay? And this mutual inductance can also be written in terms don't forget that this flux is a function of time as well, right? And I'm going to put my current downstairs. Current downstairs, okay? So, and what else I'm gonna do? Here you go. Furthermore, what else do you have? That's the parameter that we're that we call mutual inductance, okay? For a solenoid, the mutual inductance is going to be given by this equation that you see right in here. Okay, and then we can also here write one more important thing here. We can also here write that the induced voltage in the secondary coil is going to be given by this term, the right in here, right? Which, by the way, can be moved to this parenthesis, and we saw beforehand that is given by something like that. And look what we end up getting. Here you go. We end up getting a relationship that is equal to a parameter that depends on the geometry of your coil times a delta I delta T, okay? And that's where we can go back to those other two equations that you saw before. Here you go, for the capacitance and the resistance. And I'm going to write that down. It's slightly different, okay? So I'm going to write that down in terms of voltage. Since the inductance there, the induced voltage is being written in terms of what we have on the right side, I'm going to write it in terms of the voltage as well for those parameters here. Here you go, V equal to Ri, okay? So here you go. This one I'm going to write it in a slightly different way. 1 over C times Q. And I'm going to put it in the order that they appeared, okay? So here you go. This V corresponds to this V, which corresponds to this V, right? What you see right in here, 1 over C, is a parameter that depends on the geometry of your capacitor. And what you see right in here, R, is also a parameter that depends on the geometry of your resistor, okay? Geometry dependent, geometry dependent, geometry dependent, okay? Here, this Q, I'm going to here write it in a slightly correspond to this current. Why is that? Because this current can be here written as though as it is delta Q over delta T. Do you see the progression that we are getting here? And now this other current that you see right in here can also be written in terms, of delta Q, right? I'm going to put it inside this parenthesis, that's better, over delta QP. And I'm going to emphasize that not this one here, is this one that I want. Yeah, I'm going to emphasize that for the primary inductor. Okay, we can remove this one here. And now do we see how this thing progresses? We have V on the left side. We have parameters that depend on the geometry of your device. And we have another term that depends on the charge, depends on the variation of the charge. If this one is delta Q over delta T, we can write that down like as being, power to the first one, right? This one, delta T power to the first one. This one here, we can write as being power to the second one. Because I'm combining the deltas, right? That we have, here you go, power to the second one as well. So it's, and what about this one? This one, we can also write that in terms of delta Q powers as well. But the delta Q powers that we can write, this one is going to be in terms of the delta, is going to be in terms of the power to the zero. Delta raised to the zero is 1. Delta T raised to the zero is also 1. And then we end up with the Q that we had before. Do you see the progression that we are getting here? There are devices that their equations are somewhat related to each other. Note that for all these 3 different devices, we have the following parameters in common. 1, the voltage. 2, parameters that depend on the geometry of the device. In this case is the capacitance, well, actually is the inverse of the capacitance, the resistance, and the mutual inductance. And the power of the operator, the powers of the operator. delta T, delta T, right? I'm going to put the power n of the operator. So you have all those three connections between those three devices. Okay? And we can do that for the mutual inductance. I'm going to here write my mutual inductance, as we saw before, is something like that, right? N sub P is NP divided by L. I'm going to put the capital L. And that what? And they are all parameters that depend on the geometry. We can do the same thing for self-inductance. We repeat the same for self-inductance. What time is that? 12:53, right? Oh, we run out of time. Sorry, folks. And let's see. And I'm going to write that down here, the final result for self-inductance. Self-inductance, I'm going to call, and by the way, I'm going to use it lowercase l here. Lowercase l. Okay, self-inductance, and we get something like that. Okay. Sorry, I went over my allotted time. Do you have any questions about that? Okay, so you can stop here right now, and I see you on Wednesday for the next lab, which is lab number 4. Okay.
Hello.
Can I have access to lab 3? I never got it. I was absent that day.
Okay. Wait a minute, let me stop here.